Welcome. So today I want to talk a bit about hitting a tennis ball. If we examine how a tennis player hits their balls, we're going to find a few physical contradictions, and I just want to address those today and explain what's actually happening. Let's first look at some of the values that we're dealing with here. At the outside, a tennis net is a little over 1 meter tall, and in the center, it's a little over 0.9 meters tall. Now compare that to a tennis player. A relatively tall tennis player is going to have a waist height of about 1 meter. This means that most balls will be hit below the waist or below 1 meter in height. So if we look at a ball that's hit about half a meter off the ground and compare that to the height of the net, which will be somewhere between 0.9 and 1 meters, so let's say 0.91 for this example. Now if we assume a tennis player is hitting a standard ground stroke, they're going to be around the baseline, which for a regulation tennis court is going to be about 11 meters away from the net. Now, this gives us some angle that's needed for a tennis player to hit the ball over the top of the net. Now, this is an upwards angle, but if we look at the angle of a tennis ball being hit, we see that the racket face is flat and that the normal force is going directly outwards. It does not have an upwards angle. And this isn't even accounting for the necessary force of gravity acting down on the ball. The second contradiction that we're going to see here is that when we hit this tennis ball, if we find the minimum necessary angle to get the ball barely over the net and look at the initial velocity of the ball, which I've calculated based off of a standard 85 mile per hour ground stroke to be about the velocity shown on the screen, we can then do some simple calculations to find the position away from where it initially started that it will land. We find this is about 49 meters. The problem here is that a normal regulation tennis court is under 24 meters in length. So this ball is a good distance off the back of the court, even when it's being hit from the baseline. But if we take a closer look at the ball being hit, we'll first address the first contradiction, which is how the ball gets over the net at all. Now, if we watch the racket, we can see that it's moving upwards as it hits the ball. So, if we take a look at a quick force diagram, we'll see that we have a force of friction upwards, as well as the normal force outwards, and of course, the force of gravity. It's this force of friction that gives the ball all of its necessary upwards momentum. Now if we take a look a second time, this time looking specifically at the ball after it's being hit, we'll notice that it starts spinning. So we know that the ball has an upwards momentum caused by friction along its surface. But because that friction isn't applied directly to the center of the mass of the ball, but is off-center slightly, it also creates a torque around the ball, causing it to spin. Now if we look at the direction of spin, we're going to see something that tennis players refer to as topspin. This is a very important type of spin for a tennis player because it's necessary in keeping the ball on the court. And this is where we address the second problem that we see when a tennis player hits a ball, is that the ball's initial velocity, given a basic projectile motion setup, would suggest that it should leave the court, but in fact it doesn't. See, this topspin that tennis players generate creates what's called the Magnus force, which is a force exerted by air resistance on a spinning sphere while it's traveling through air. Now that force goes with an equation of S times the cross product of omega and the velocity of air relative to the object. Now if we think of the tennis ball at rest, then we can say that the air is moving in the opposite direction of the tennis ball's velocity. This means that we end up with a cross product that gives us a downward and forward pointing force when the ball is on the front part of its arc, and a downwards and backwards facing force when the ball is at the back part of its arc. This additional force is what in fact keeps the tennis ball on the court. Now, to calculate the exact magnitude of this force, we would need to know what that coefficient S was. However, there's no real way to find that apart from trying to measure a tennis ball's air resistance in a wind tunnel, and that needs to be measured at many different rotational frequencies as well as at different velocities. It would also require that we measured along different axes that the ball could be spinning on, because tennis balls are not perfectly symmetrical. The lines in them can affect how they interact with the air, as well as you can get different effects created by either smooth or turbulent air forces. So calculating the exact force of topspin is a challenge, but we do know the direction it points, and the ball actually ends up being pulled towards the net at all times. This means it not only gets over the net faster, but on the back side of the court, the force pulling it towards the net helps keep it on the back of the court. I'd just like to take a second here at the end to thank my professor, Dr. Amy Kolan, the entire physics department here at St. Olaf, as well as the Digital Scholarship Center here at St. Olaf. Without them, this video couldn't have been possible.